In previous videos, we looked at fixed points and stability for single variable difference equations, and we saw that we could use the derivative of the equation to help us determine whether we thought the system was going to approach the fixed point in the long run. Now, when you have multiple variables that are changing, when you have a system of difference equations, things get a little bit more complicated. And so what I want to do in this video is I want to look at just a simple linear system of the form xn plus 1 equals a xn. And I want to see if we can figure out what's going to happen in the long run. And then in the next video, we'll look at how we can take that idea of what happens for a linear system and then use that to understand how nonlinear systems are going to behave. All right, so first of all, let's assume that, again, x is a vector and a is a matrix. And so the way that we compute the new value of x is we multiply the old value of x by a matrix A. And so x1 would be equal to a times x0. x2 would be equal to a times x1. And since we already know x1, we can actually think of that as a times x0, which is going to be a squared x0. And if you continue that pattern, what you'll find is that the analytical solution is a to the n times the initial state gives you the value of x after n steps. Now the problem is, unlike a constant, like we had in our single variable examples, it's harder to say what's going to happen as you multiply a matrix by itself over and over and over again. Is that going to go to 0? Is it going to go to infinity? Is it going to bounce around? And in order to be able to figure out what happens to x, we do really need to know what that matrix does. And so we're going to need to draw in some tools from linear algebra. And the first concept we're going to use is what's called diagonalization. In diagonalization, we say the following. A matrix A can be written in the form A equals some matrix P times a diagonal matrix P, D, times the inverse of P, where P has columns V1, V2, up to Vn, and these are called the eigenvectors of A. And D is the diagonal matrix, looks like lambda 1, lambda 2, all the way up to lambda n, with zeros elsewhere. And lambda I is called the eigenvalues of A. And this is not always true, but it is true if D or if A is n by n and has n eigenvalues. All right, so for most of the matrices that we will encounter, we will be able to do this. We'll be able to write A as a product of 3 matrices. And the way that you compute those matrices is you compute the eigenvalues and eigenvectors of A. Now, I'm guessing some of you may be a little rusty on how you compute eigenvalues and eigenvectors, or even how they're defined. So let's quickly refresh our memories on that. All right, so if lambda is an eigenvalue, then what we mean is that A times the eigenvector is equal to lambda times the eigenvalue. Okay, so these vectors and these values come in pairs. Each eigenvalue has a corresponding eigenvector. And they have this property that when I multiply my matrix A by V, the eigenvector, it's the same thing as if I just multiply that vector by a constant factor, lambda, the eigenvalue. And you can find eigenvalues by solving the determinant of A minus lambda I equals 0 to get the eigenvalues. And then once you've got the eigenvalues, you can solve A minus lambda I V equals 0 to get the eigenvectors. All right, so let's do a quick example of that, and then we'll see if we can understand how this diagonalization helps us. So suppose A equals the matrix, let's just pick something simple. Let's do, how about 1, 2, 0, 3. All right, let's see if we can find the eigenvalues. And so what we're going to start off by doing is computing the matrix A minus lambda times the identity matrix, which would be 1, 2, 0, 3 minus lambda times the matrix, and the identity matrix has just ones along the diagonal, which would be, if I group all those together, we'll have 1 minus lambda, 2, 0, and 3 minus lambda. And if you take the determinant of that, the determinant is just the product of the diagonal entries minus the product of the off-diagonal entries. And in this case, we get 1 minus lambda times 3 minus lambda. And the other term is just 0. And at that point, we're interested in where that's equal to 0. And notice, by leaving it factored, it's very clear. Lambda must be equal to 1, or lambda must be equal to 3. Those are the two eigenvalues for this matrix. And once we've got our eigenvalues, we can start to find the eigenvectors. A minus lambda I, well, if I plug in lambda equals 1, then A minus lambda I is just equal to 0, 2, 0, 2. And so we need to solve that equation up top, A minus lambda IV equals 0. So 0, 2, 0, 2 times a generic vector, and I'll just fill in some components. We'll call it, how about x and y? And that needs to be equal to 0. Well, if we write out those equations, we get 2y equals 0 and 2y equals 0 from the first row and the second row. And so therefore, y is equal to 0. And x could be anything. And that's actually not a coincidence. Whenever you're computing eigenvalues and eigenvectors, the eigenvectors are not unique. You can multiply them by any constant, and it would still be an eigenvector. All right, so our eigenvector must have the form, there's some x, which let's just pick an x value of 1 to make things simple, and then the y value must be 0. And then for lambda equals 3, A minus lambda I would be equal to, let's scroll back up. We're plugging in 3 there, and so we'll have 1 minus 3, 2, and 0, 0. And so our system of equations is just negative 2, 2, 0, 0 times xy equals 0. And so our equations are negative 2x plus 2y equals 0 and 0 equals 0. And again, you'll notice we really didn't get two useful equations. We only got one. And that first equation can be rewritten as just x equals y. And so we are free to choose x. And once x is determined, y will be the same thing. So one example of the eigenvector would be 1, 1. All right, so there's our eigenvalues and our eigenvectors. And what that means is our original matrix, which we had wrote as 1, 2, 0, 3, if I'm recalling correctly. This can be written as P, D, P inverse, where P is the matrix of eigenvectors. And so I'll put 1, 0, 1, 1. Those are my two eigenvectors. Each one gets their own column. And then D is a diagonal matrix, and it has the eigenvalues along the diagonal, and they need to be in the same order. So we had lambda equals 1 was our first eigenvalue, and lambda equals 3 was our second. So there's our diagonal matrix, and then we just need the inverse of that first matrix. And the claim is that those two things should be the same. And let me bring up Octave, and we'll check that really quickly. All right, so bring up a new example. All right, so we want to take P is going to be 1, 1, 0, 1. D is going to be equal to 1, 0, 0, 3. And so if we multiply P times D times the inverse of P, notice we get exactly what we hoped for. You could do the matrix multiplication by hand, but to save time, I've done it with the help of Octave. And in fact, Octave can also be used to compute eigenvalues and eigenvectors. So let's define A to be the matrix we are interested in, 1, 2, 0, 3. If you compute, say, just EIG, I of A, notice it gives back 1 and 3. And if you want to compute the eigenvectors and eigenvalues both at the same time, we can type bracket V comma D. And what that does is it give you a matrix where each column is an eigenvector, and then the diagonal matrix D, which has all of the eigenvalues. And notice their eigenvectors are a little different than ours. The first column is 1, 0, which is what we found, but their second one is 0.7, 0.7. That is just a scalar multiple of the eigenvector that we found, and it is equally valid. They just found a different but equivalent way of diagonalizing the matrix. Okay. All right, so I know that was a very quick refresher. If you're rusty on eigenvalues and eigenvectors, I will post a link to some YouTube videos from linear algebra that might help give you some more practice with that. But let's move on to see how we can actually use this to help us with our difference equations. All right, so what we argued is that most of the time, we can rewrite our matrix A as P, D, P inverse. And when we have the difference equation xn equals, or xn plus 1 equals a times xn, the analytical solution was the nth value of x was a raised to the n times the initial state. All right, so put that back on the screen here. All right, so that's where we started. We were looking at a difference equation. We said the analytical solution is a to the n times x0, and now what we've argued is again that we can diagonalize the matrix. So let's think about a to the n, given that a is just P, D, P inverse. Well, when you raise a matrix to the n, that's just like multiplying by itself n times. And so this is just P, D, P inverse times P, D, P inverse, a total of n times. And what I want you to notice is that in the middle, we have a bunch of products of P inverse and P. Well, when you multiply a matrix by its inverse, what you get is the identity matrix, which doesn't change anything. And so we're going to have a whole bunch of P inverse P's in the middle that are all going to cancel out. And so this is ultimately going to simplify down to just P times D to the n, P inverse. And D to the n, if D looks like lambda 1, 0, 0, lambda 2, then D to the n is actually a very easy matrix to compute. You just have to take each power to each eigenvalue to the nth power. Okay? All right. So what that tells us is if we go back up here, this can be written as P times lambda 1 to the n, lambda 2 to the n on down, times P inverse times our initial state. All right, and this is the key point. If we want to know what's going to happen in the long run, it's the eigenvalues that are ultimately going to make the difference here. If the eigenvalues are all small numbers, if they're all less than 1 in absolute value, what you'll find is that when you raise them to a large power, they're going to get smaller and smaller and smaller. So if the absolute value of lambda I is less than 1 for all I, then that matrix in the middle is going to get closer and closer to a zero matrix. And what we can conclude is that xn approaches 0, right? Because on the right-hand side, we're just multiplying the initial state by a 0 matrix in the long run, and we're going to get 0 no matter what you multiply a 0 matrix by. Okay? On the other hand, if the absolute value of lambda I is greater than 1 for any I, then what we'll see is that that particular term in the matrix is going to get bigger and bigger and bigger. If you take a number bigger than 1 and multiply it by itself over and over and over again, it grows. And then we would say that xn diverges as a result. All right, so if you're multiplying by something that's going off to infinity, well, then the solution is going to have to go off to infinity as well. So ultimately, if we want to figure out what happens in the long run with a linear system, what we need to do is find the eigenvalues of the matrix A. We need to look to see if they are all less than 1. If they are, then we can be confident that our solution will go to 0. And if they're not all less than 1, then our solution is going to diverge. And we will take that idea and extend it to nonlinear systems in the next video.